Hi everyone, my name is Britney Dahana Rives, F25S179, and today I will be presenting my bioscience project titled Durian Musangking D197 Growth Modeler. This interactive HTML project combines bioscience, agriculture, and calculus to model growth dynamics of Musangking durian fruits. The model helps us understand how the fruit grow over time and how mathematical calculation can be used in agro-product technology. Summary of the chosen bioscience problem. The bioscience problem chosen in this project is understanding and predicting the growth pattern of Musangking durian fruits. In agriculture, farmers need to know how fast the fruit grow. When growth reach its maximum rate, the best time for nutrient management, the most suitable harvesting period. The HTML use a logistic sigmoid growth model to simulate the increase in fruit weight from fruit set until maturity. The model is represented by the equation. You can see the equation. The graph also shows the growth velocity using the first derivative of the equation. Importance of studying this bioscience problem. Studying this bioscience problem is important because first, it helps farmers predict fruit development more accurately. Second, it allows better fertilizer and irrigation management during critical growth stage. Third, understanding growth kinetics help improve fruit quality and reduce psychological disorder such as hollow plum formation. And finally, it supports efficient post-harvest planning, ensuring fruit are harvested at the optimal maturity stage of market distribution. Therefore, mathematical modeling can improve both agriculture productivity and fruit quality. Okay, this section explain the biological background of Musangking growth. It states that monitoring fruit weight accumulation over time helps predict the nutrient requirement, fruit maturity, harvest scheduling, supply chain management. This shows the connection between bioscience and agro-product technology. On the mathematical foundation, this section introduces the logistic growth equation. The model divides fruit growth into three stages. The first is late phase, second is linear of exponential phase, and stationary or maturity phase on 17 until 19 days. This makes bioscience concept easier to understand visually. This section translates mathematical result into practical agriculture meaning. For example, during the late phase, irrigation is critical. During the rapid growth, nutrient demand is highest. During maturity, harvesting decisions become important. This helps users understand the real-world significance of the calculation and recommendation to improve the HTML. One improvement I would recommend is adding real mosaiking for image at different growth stage. The benefit is make the interface more attractive, help user relate the graph to actual fruit development, improve learning and visualization for students. Alternatively, the HTML could include growth stage animation, comparison with other durian varieties, weather and environmental factor simulation. So the conclusion is this HTML successfully combines bioscience, agriculture, and calculus to model mosaiking fruit growth. It helps users understand growth kinetics, nutrient management, and harvesting decision through interactive visualization and mathematical analysis. Thank you.
So next, Arif, you can present
Uh,
your grapheme.
Hi everyone. My name is Muhammad Ari Irfan bin Azhar, F251881. Today I'm going to present about kinetic of protein production, aquaculture's growth derivative model. Firstly, the Malaysian food security context. Under Malaysia's National Agro-Food Policy 2.0, aquaculture is marked as a critical high growth sector to meet the target self-sufficiency level (SSL). For fish proteins, feed costs account for up to 17% of total production cost in red tilapia cage farming. A central challenge in bioscience resources planning is modeling growth velocity. Farmers cannot easily determine when growth rate peaks by looking at cumulative weight graph. By using the first derivative of the logistic biomass curve, bioengineering can look at the exact inflection points, the precise moments of maximum growth velocity. Next, cumulative fish biomass. F columns X equal to 600 per 1 plus E minus 0.25 columns X minus 12. And then instance growth. F columns X equal to 150 points E minus 0.25 column X minus 12 per column once plus E minus 0.25 column X minus 12 power 2. Okay, so you can see at the graph, this is the individual fish weight gram grow on 550 gram and for instantaneous growth rate gram. Grow rate gram per week. Grow on 35 gram, but it decreases on 5 gram again. Next, in conclusions, tracking total Cumulative weight over a 24 weeks cycle provide a general overview of fish growth. Applying calculus through the fish derivative equations unlocks the critical insight needed for efficient farm management. By identify that the fish reach their peak growth velocity of 37 per 5 gram per week at exactly week 12. We can pinpoint the precise moment the fish are developing the fastest. Practically, this allows farmers to target intensive feeding right when metabolic rates are highest, significantly reducing food waste and cutting down major production costs. So that's all from me. We go to the next presenter.
Uh, Hi everyone. A very good evening to my friends and my lecturer. My name is Sreethar and I'm majoring in agro product technology. Today I am excited to show you that calculus is not just abstract equation on a whiteboard. It is a vital tool for modern and value precision agriculture. Specifically, we will explore how we can use differential calculus to monitor and optimize the growth kindness of Malaysia's pride, the Musang King D197 durian. In premium orchard management, guessing is no longer acceptable. The Musang King trees takes years to yield, and each fruit is highly valuable for it. If we do not understand exactly how the food is expanding, we cannot accurately schedule the irrigation and apply the potassium rich fertilizer or predict harvest yields. Historically, farmers only monitor total size, but as food technologists and agronomists, we need to look deeper. We need to measure the instruction rate of change, which is the physical growth speed in grams per day. And mathematically, that growth speed is represented by the first derivative. So you can also see my graph and the mathematical calculation. Here, L is represented that carrying capacity which we set to 200 grams that typically weight of a mature Musang King. The term is our growth constant at 0.08 and XO is the inflation point set at 60 days. And also you can see at day 15, we see the mass is only around 43 grams and the derivative is a teeny 3.3 gram per day. Biologically, this is the lag pace. Cells are dividing internally, but the food isn't swelling yet. Fertilizer here should focus on phosphorus to secure stem strength. And now watch that happens at day 16. This is the mathematical inflection points where the curves shift from concave up to concave down. Here our derivation peak at exactly 40.5 0.00 gram per day. This fruit is growing at maximum speed. If trees face water stress or nutrient deficiency right now, they will stop fruit permanently. Agronomists must supply peak potassium and consistent water at this exact critical shoulder. This model isn't just a mathematical toy. It is calibrated against development indicators by the Malaysian Department of Agriculture in their page, as well as Magdi's physical economy characterized research on Mozambique. By, by this point, agro-product industry can automate smart irrigation system that release water population to design smart fertilizer schedule and calculate the logistic and market delivery timeline week before the food drops naturally. And you can see in conclusion, calculus provides the precise language needed to decode biologically by converting static observation into dynamic rates of change throughout the derivative of F1. We bridge the gap between pure mathematics and handed-on agrobiotechnology. Thank you for your time. I'm now open my presentation to Dini.
Hello everyone, my name is Nurdini Amani binti Azman. My metric number is F25B1689. Today I will present our project title is Biopest Cancellation Simulator. Is interactive deviation analysis of MD2 with pineapple waste fermentation. This project show how calculate, especially the first derivation can be used to analyze lipid acid production from MD2. Pineapple waste starch or fermentation. The simulation uses a logistics segment model to precise lipid acid concentration over time. The division function F is used to calculate the production rate at a specific time. The graph show to change in lactic acid contraction from and production rate during the fermentation process. User can also adjust differentiation permutation to observe the effect to the result. Based on the simulation at 16 hours, the lactic acid contraction is 22.50 gram liters, and the production rate is 2.03 gram liters. This interested that the fermentation process is our operating efficiencies. In conclusion, the simulation help user understand the application of calculus in biopest in direction of fermentation analysis to MD2 pineapple waste. That's all from me. Thank you.